Hello everyone, and welcome to Everything's Relative with me, Mr. K. Today we will be doing a crash course on the topic of alternating currents for Cambridge or CAIE Physics, A-Level Physics 9702. Now, alternating currents used to be a part of magnetic fields, and the topic itself is usually now done after magnetic fields, and on its own it is a fairly short standalone topic, but there are still some concepts that can make this a little bit complicated. So in this crash course, we will try to summarize those concepts as briefly as possible while still getting the important information to you. Now, you may remember from AS Physics the topic of direct currents. So what we'll do is a quick recap on the topic of direct currents before we talk about alternating currents. So let's refresh our memories on direct currents, and for future reference we'll call this DC for direct current. Let me draw a conducting wire, a one-dimensional long conducting wire with charge carriers carrying an electric current. We know a current is simply the movement of charge. So this is my conductor. Could be copper as an example, and in the conductor my charge carriers are electrons. Now for direct current, what I have is that all of these electrons are moving in the same direction and they're all moving at a steady rate. That's important. So my current is steady and the movement of electrons is in one direction. And guess what? The motion of the energy, the electrical energy, is in the same direction as the motion of the electrons. And so energy is carried from one point to the other. The electrons move in one direction and they all move at a steady rate. And so the graph of current versus time, if I were to plot this graph, or sketch this graph at least, would be fairly uninteresting. So I against T for a DC current would just be a meant to be straight enough. It's a straight horizontal line. It has a value, let's call it I naught, doesn't really matter what we call it, but that value is constant. This current does not change with time, and it turns out that the voltage is the same as well. This is a simple circuit. In a simple circuit, the current isn't changing, and the voltage isn't either. Okay, so that's what we remember from the topic of direct currents. Now, in alternating currents, things are slightly different. Actually, quite different as it turns out. But let's talk about what an alternating current looks like. Now, you may have had experiences with this, but they may have very well been fleeting. Alternating currents we will refer to as AC going forward. Again, we are physicists. It's our duty to be as lazy as possible. So an alternating current, I'm going to draw the same diagram. I'm going to draw a thin, long conductor, and I'm going to draw my charge carriers inside the conductor. So this could be the same conductor. We don't need to change conductors for AC or alternating currents. I also have the same charge carriers. So these are electrons. So what is different about AC? Well, it turns out that instead of moving in one direction, alternating currents occur when electrons oscillate about some fixed position. They move back and forth, as I'm drawing in the diagram. So the current is actually moving about a fixed point and not moving in a steady single direction. This is very different to direct current. So what happens is that the electrons, and hence the current, constantly reverses direction. The current is not steady, the direction is constantly changing. The good thing though is that the energy at least flows in one direction. So it flows from high potential to low potential, and that still means we can transport electricity long distances using AC. In fact, it is preferred that we use AC to transport electricity long distances because it turns out that AC loses less energy, loses less heat to the surroundings when transporting electricity long distances. That's basically the main use of AC, to transport currents long distances. So thankfully the energy still flows in one direction, from the substation to your home. Now if I were to plot a graph of current versus time, it's going to look a lot different from the graph we've drawn before, because the current is constantly changing direction. And so let me sketch a simple graph of current versus time for an AC current. Now, since the current is changing direction, I have to make sure that there's a negative axis. And if at time t is equal to 0, the current hasn't started yet, I can start this graph from 0. And it turns out this graph will have a sinusoidal shape, or cosinusoidal shape, if I start my stopwatch at any other time. So this is very similar to the graph that we've seen in the topic of oscillations for simple harmonic motion. If we look at the electrons, the motion that they are exhibiting is very similar to that of sound waves. For sound waves, the air molecules vibrate about a fixed point, but the sound wave and the sound wave energy travels from source to target. So it's a very similar idea, and it turns out that some of the equations will be analogous to those that we learn in waves. Now, before we go any further, let's define some of the properties of this graph. The maximum value, be it positive or negative, so this current fluctuates between I0 and minus I0. Again, the direction is simply arbitrary. We choose a preferred direction and call it positive, and the opposite direction will be negative. We call this maximum value the peak current. Peak is simply another word for maximum. We can also say current amplitude, or we could simply say maximum current. We have to define another quantity which is specific to AC and specific to cathode ray oscilloscopes, which we'll talk about a little bit later on. But a cathode ray oscilloscope doesn't have a nice set of axes. We simply see a sine wave, and that sine wave can be shifted and moved around the screen. So measuring a peak current will be difficult because you wouldn't know where the central point is, where the x-axis is. So what we do is we measure the distance from a crest to a trough, from the topmost peak to the bottommost peak, I0 to minus I0, and the magnitude of that value, the size of that value, is what we call a peak to peak current. It's simple, we're going from one peak to the other, and so we call it the peak to peak current. And there's a simple relationship between this. We can see that the peak current is related to the peak to peak, where the peak current is half of the peak to peak value. So the peak current is the peak to peak current divided by 2. That's the relationship between the two. So if I ever wanted to find the peak current, I can find the peak to peak by measuring the separation between the crest and the trough, the bottom and the top, and divide that number by 2 and get the peak or maximum current in the circuit. Remember, the electrons are moving back and forth, and so they can only gain a certain speed, move at a certain rate, before they slow down, stop, and change direction. So if I wanted to describe this mathematically, just like I did for the topic of oscillations, the general form of an oscillation, x is x naught sine omega t. So what I need is for my current to be oscillating. Current is represented by the letter I. So I is I naught sine omega t. It turns out that the voltage is also oscillating. And so we can write the voltage as a function of time as V naught sine omega t. So I have two equations here that describe how the current changes with time and how the voltage changes with time. It turns out they both oscillate. So Who would have thought? But moving the electrons back and forth has a very significant outcome for the current and the voltage. Now, before we go any further, let's define some of the quantities to remind ourselves of this motion. Now, omega, we simply can't forget what omega is. T is the time, I naught is the peak current, V naught is the peak voltage, the maximum of each quantity. Omega, if we remember from waves, is 2 pi times the frequency. And the frequency of a signal, if you're in the US, the frequency is simply the number of times per second that the current changes direction. It does so 60 times per second in the US and 50 times per second, I think, everywhere else. And this frequency is equal to the angular frequency, which is the name for omega, divided by 2 pi. And so if I recall my units, I'm going to use square brackets to denote units. So square brackets F means units of F is simply the hertz, or per second. Just like waves and oscillations, the angular frequency omega is measured in radians per second, and the period t is measured in seconds. Now, we didn't derive these equations for I and V because they require a little bit of calculus. Actually, turns out quite a bit of calculus. And since the course is not a calculus one, we just have to look at the shape and realize that that shape is associated with the equations of this shape, something sine omega t, and that something is the amplitude of whatever is changing with time. Current amplitude and voltage amplitude, I naught and V naught. So that's an introduction to what an alternating current actually is. Now, normally in a crash course, I wouldn't spend time doing an example, but in this case, I think an example on the cathode ray oscilloscope would be quite handy, especially because many exam questions deal with cathode ray oscilloscopes, and reading them might not be obvious, especially if you haven't seen one in real life. So let's do an example on the cathode ray oscilloscope that looks as follows. And so, like magic, we have an example on the cathode ray oscilloscope, or CRO. Now, this example has a graph of current versus time, I versus t. We are shown the signal on a CRO, the trace, if you will, on the screen of a cathode ray oscilloscope. And we are told that an alternating current is connected to the input of the CRO. The time-based setting is a millisecond per centimeter, and the voltage control is set to 10 millivolts per centimeter. We are asked to calculate the frequency and the peak voltage of the signal. So let me go about trying to solve this problem. So I need to first find the frequency. Now, looking at this, it's quite difficult. How many times is this wave changing direction per second? What I can see, or can determine quite easily from this graph, is the period. The amount of time it takes for a full cycle to occur. So the equation for frequency, F, we know is 1 over the period. So let's find the period. So the period of oscillation is the time it takes for an electron to do one complete motion, to move to one side, move back to the equilibrium position, and then get back to where it started. Now, I don't have an x-axis that is measured in seconds. I'm given centimeters, even though I'm supposed to be measuring time. But I am told that every centimeter on the x-axis, in this case, is represented by 1 millisecond. That's what the time-based setting means. So what I have is 1 millisecond for every centimeter, and then I can multiply it by this distance, which is 2 centimeters. Why am I multiplying it by 2 centimeters? Because a complete cycle that I'm highlighting now happens in 2 centimeters. And it turns out this pattern is repeating. Every 2 centimeters is a complete cycle. So the period is the time taken for a complete cycle. 1 millisecond per centimeter times 2 centimeters. Calculating and keeping note of my significant figures, I get this to be 2 times 10 to the minus 3 seconds, or 2 milliseconds. I simply wrote milli as times 10 to the minus 3. That means I can now go and find my frequency. My frequency is 1 divided by 2 times 10 to the minus 3, and this gives me a frequency of 500 hertz. 500 per second. And so that's the frequency of this AC signal. Not too bad, now was it? The second part of the question tells me you're not done yet. You need to find the peak voltage of the signal, and the voltage control is set to 10 millivolts per centimeter. So even though my y-axis, so this is actually voltage versus time, current versus time, so V against T, still has the same shape. This is what you would see in an oscilloscope. You'd see a sinusoidal shape, and you'd be measuring the voltage. So instead of being given volts, I'm given centimeters, but I have a conversion to go from centimeters to volts. 10 millivolts for every centimeter. And I want to find the peak voltage. Now, I can see that going halfway from peak to equilibrium is 1 centimeter, which means that going from peak to peak is 2 centimeters. Now, ideally, I drew the diagram in a very specific way to label this 1 centimeter, but it wouldn't be that easy for you. You'd have to measure the peak to peak because this value of 1 wouldn't be given to you. So, to be safe, we always measure the peak to peak voltage. So I'm going to call it V subscript peak to peak. That's a long subscript. And this is 10 millivolts for every centimeter multiplied by the peak to peak distance, which is 2 centimeters. And this is 20 millivolts. A centimeter is simply the distance on the screen. Sometimes also referred to by a division. Each division is a centimeter in size. And so the peak voltage is simply the peak to peak voltage divided by 2. So I'll call it V naught, again, simply because I'm lazy and because I can. 20 millivolts divided by 2. The peak voltage of the signal is 10 millivolts. And so that's a simple example on the cathode ray oscilloscope. So CROs are very important. And like I said, I normally wouldn't do an example in a crash course, but since it's so common, it's important to see what a CRO output would look like and what the questions could look like. Now, obviously the questions could change, but if you've never seen a CRO, it's good to have an idea of what the screen would look like. My suggestion would be to have a look at maybe YouTube videos, etc., to have an idea of what a cathode ray oscilloscope looks like. So, moving on, let's talk about something that may be familiar to you, RMS values. Now, you should have done the topic of ideal gases, and the abbreviation RMS should hopefully ring a bell. Now, we're talking about RMS values for AC. Okay, so it's slightly different to ideal gases. Now, if I go all the way back, look at my voltage versus time graph. If I go all the way back, look at my current versus time graph. Both are sinusoidal. Both where the x-axis or the time axis is the central point of the graph. So what does this mean? This means that my average value of my current is going to be right in the middle of the peak and the crest, or the trough and the crest. That middle value is 0. So using average values of currents, not very helpful, is it? I mean, if I want to calculate the average current, it's always going to be 0. It's going to be the same with the voltage. Not very helpful. So let me redraw my sketch of I against T. So current versus time, there is a sinusoidal oscillation. Great, and I can see that the middle value is simply the time axis, so I is equal to 0. So the current spends most of its time on average at the 0 point. So if I were to change this graph slightly, instead let us plot a graph of I squared against time. I squared can never be negative. The square of a number can never be negative. So what I should get is a very similar, again not drawn to scale. I'll still get the same shape. And if you want to square the function with its sines and cosines, by all means do so. But it's obvious that this graph will be placed on the time axis. It will always lie on or above the time axis. The new peak value is no longer I naught, but I naught squared. Aha! So now let me find the average of this graph. Now the average value, which I'll represent by triangular brackets like we did for ideal gases, is a half of the square of the peak value. A half of I naught squared is right in the middle. That's where my average value should lie. So why is this important? Let me take the square root of both sides. The square root of I squared, I naught squared under a square root sign is simply I naught, and that's divided by the square root of 2. Aha! But this thing on the left hand side, the square root of the mean value of I squared, by definition is the RMS value if you do statistics. So the RMS value for the current is I naught, the peak current, divided by the square root of 2. And it turns out that the RMS value of the voltage takes the same shape. V naught divided by the square root of 2. And so we have two more equations that are very important. The RMS values are different from the peak values. And obviously we can see that the peak value I naught is bigger. So it's root 2, which is a number bigger than 1, multiplied by the RMS value. So remember that your peak value is always the peak, the maximum. So RMS must be the smaller one. Now, why is this important? Well, simply, I'm just going to state this. The RMS value of the alternating current or voltage is that value of the direct current or voltage that will produce thermal energy at the same rate in a resistor. So all this means is that if 100 watts of thermal energy is being produced by a 2 ampere current, a 2 ampere direct current, then a 2 ampere RMS current will produce that 100 watts. So RMS is sort of analogous to the current in DC. So where the current would spend, in air quotes, the most time. Okay, because it's oscillating between values, it will spend the most time at the RMS value. One more thing we need to talk about is the power. Now power, if we again go back to our knowledge of electric circuits, is voltage times current, V times I. So an RMS power would be VRMS times IRMS. Now if I go to the equations above, this is peak voltage divided by root 2 times peak current divided by root 2. Aha! So what I get is V naught times I naught, and don't tell anyone, but the root of 2 times the root of 2 is simply 2. So I get a half V naught I naught. Interesting? Turns out it is, yes, because V naught times I naught, peak voltage times peak current, is peak power. So the RMS power looks slightly different. The RMS power is half the peak power. And so that's why we use the two relations to show what this power would be. So on average, the maximum, half the maximum power would be the RMS power. And so the RMS power looks slightly different to the RMS voltage and the RMS current. So that's just a little bit about the important equations when it comes to RMS values. And don't forget power. Okay, power is the rate at which energy is being transferred. Now, the next thing, which is the last part of the topic that we have to talk about, actually we'll break it into two parts: the rectification and smoothing. We'll start with the rectification. Now, what is rectification? Well, in English, rectification means, well, to rectify something is to put things right, to correct an error, or simply to make things upright. I think it's the second meaning in this case. Simply, all we want to do is to convert AC to DC. AC is great because, like I said, we transport currents long distance. DC would lose a lot more energy to the surroundings, a lot more energy in the form of heat. But our devices, our laptops, our phones, etc., these devices we can't live without, they require DC to be powered. They require DC to be charged. All our devices, all our appliances require DC. I'm getting AC at the mains, but I need DC in my devices. So somewhere in between the mains and my device, there has to be a conversion from AC to DC. And so the first way we can have this conversion done is by a process called half-wave rectification. So this process is probably going to be novel, even if you have studied electric circuits and read up on AC before. Half-wave rectification is an application that allows us to convert AC to DC. And so, like magic, I'm going to show you what this looks like. As promised, here's the magic. This is an electric circuit. I have an AC power supply on the left. I have a resistor, we'll call the resistor R, on the right. And we have a diode. The triangular thing is a diode. If you haven't seen a diode before, what a diode does is allow current to flow in a single direction. It only allows current to flow in the direction of the arrow, meaning if the terminals are connected the other way, current cannot flow against the direction of the arrow. Now, why is an AC input important? Well, remember, AC is current that changes direction so many times per second, 50 hertz in most of the world, 50 times per second. What this means is that the terminals of this AC power supply also changes direction. There isn't a permanent positive or negative. They constantly flip. So let me assume that initially the top terminal is positive and the bottom terminal is negative. Conventional current flows from positive to negative. So a current leaves the AC power source, gets to the diode, it's moving in the direction of the diode, so all is well, moves through the resistor and back to the power source. Okay, so nothing untoward happens. The current flows in a straight line through the resistor, and across the resistor I measure an output voltage which I'll call V subscript output. Now let me change the terminals. So in the first half cycle, the top terminal is positive and the bottom terminal is negative. But in the next half cycle, to complete the cycle, I have to go positive and negative. The next half cycle, the top becomes negative and the bottom becomes positive. This fluctuates. It's an AC power source. But now this means that conventional current will flow in the opposite direction. So it would want to flow down through the resistor and, oops, there's a problem. It's not going to get through the diode because it's moving against the direction of the arrow. So current does not flow in the reverse half cycle, only flows in one direction. So let me sketch some graphs to understand what's happening here. My input voltage, V input, is the voltage that I'm getting supplied by the AC power source. If I plot that against time, this is what I get. Sinusoidal. Remember, AC power sources will always be sinusoidal. But something a bit weird is happening here. The diode is allowing current to flow every half cycle, but the reverse current is not being allowed. So for half a cycle, nothing happens. So if I were to measure the output voltage and plot that as a function of time, something weird happens. The backward cycles or the reverse cycles get cancelled. And so all I have are the hills and not the valleys. Again, poorly drawn. I'm a physics teacher, not an artist. So the valleys have now been completely removed, and all I am left with are the hills. So for some span of time, which I'm shading in now, no current, no voltage. When the terminals have flipped, I get nothing happening. So what have I done? In a very weird way, I've actually created DC current. DC simply means that the electrons are moving in one direction. So it turns out the electrons can only move in one direction. They can only move with the diode to the right as we look at it, or clockwise rather as we look at it. But the reverse cycle is blocked out. So there is a current. It is technically direct, but it's nowhere near being ideal. It increases, it slows down, it stops, takes a break, and does the same thing again. So the problem with this is it's clever. We don't have AC, we can't really damage our devices, but nor can we do significant amount of charging to the devices. And so the main problem with this is that there are long times with no current. So it's better than AC, but still not ideal. So there's a long time periods where there's no current. So is there a way to rectify this? No pun intended, but there is a way to correct this with something slightly more clever, which I'll do more magic to show you. So, magic completed. This weird diagram here is what we call a full wave rectifier or a bridge rectifier. And this process is called full wave rectification. So there's no need to be afraid. Well, be slightly afraid. This is a little bit tricky, but I promise this is as tricky as it gets. I have an AC input. I have 4 diodes instead of 1. I've labeled them as well. Also labeled them with different colors. Now this is not to be fancy, but there's a specific purpose that will become known soon. And I also have a resistor, R, and some output voltage across the resistor. Now what is happening here? Remember, my goal, if we scroll back up, my goal was to convert AC to DC. And so this rectifier, half-wave rectification was fine, but not great. Full-wave rectification hopes to mend this problem. Now again, if we remember from previously, the AC input, the terminals flip every so often, right? 50 times per second. Important? Well, let's assume in this case that in the first half cycle, P is positive and Q is negative. So what happens? Current moves through the circuit from positive to negative. The current reaches the bridge. We'll call this the bridge. This is a bridge rectifier. It can't flow through 3 because that would mean going against the diode. It can flow through 2. So it goes through 2, and it can't flow through 4, which will be against the direction of the diode. It then continues through the resistor back into the bridge. Now, as it gets to the bridge, it can go through either 3 or 1, but it actually can't go through 3 because it would simply follow its same path. It would have infinite energy and it continue this loop indefinitely, which is not possible. It needs to get back to the terminal, to the negative terminal. So it will flow through diode 1 and simply go back to the negative terminal. And so we've traced the direction of the current when P is positive and Q is negative. Makes a complete loop of the circuit. Now, in the next half cycle, P becomes negative, but Q becomes positive. And what this means is that the current changes direction. So the current moves in the opposite direction and enters the bridge. When it enters the bridge, it can't pass through 1, but can pass through 4. It can't go through 2, and so it moves into the resistor, just like in the previous half cycle. Notice the direction of the arrows here. It then enters the bridge again, but it can't flow through 1 because it means, again, it would be tracing the same path indefinitely. So where it can move is through 3. And it has to go to the now negative terminal, which is P, and it arrives back at this negative terminal. So in the second half cycle, it moves through diodes 3 and 4, whereas in the first half cycle, it went through 1 and 2. Now, for all of this, there's something very important that's happening. Notice the direction of the arrows at all points being against each other, but the direction of the arrows through the resistor are in one direction. The current only flows in one direction through the resistor. If I measure the output voltage through this resistor, it will be DC, positive to negative. It will only be in one direction. This is a DC output because current is only flowing in one direction. And so it turns out that we weren't just putting together stuff to make a pretty circuit, but actually there's a purpose. AC goes in, DC comes out. This is called full wave rectification. Why is it called full wave rectification? What we've done, remember V input is sinusoidal. The input source is always sinusoidal. But the output is what we are really interested in, the DC output. So if I measure the voltage across the resistor, something very similar to half-wave rectification, but I've taken my valleys and turned them into hills. I've taken away the negative current and replaced it with positive current. So I'm not losing half a cycle. Even when Q became positive and P became negative, I still had current moving through the circuit. And it always moves across the resistor in the same direction. So again, very poorly drawn. This is what the full wave rectification graph looks like. Voltage against time is a series of hills and no valleys. We've taken all the valleys and flipped them over the time axis to be positive. And so what I've done is I've rectified the current. All the current is now pointing in one direction. I can use this current to charge my devices. I have a bit of a problem though. I still have a little bit of an empty space between hills. A lot less than before, which is great. My current is still fluctuating a bit too much. So better, but not ideal. Now, the last part of this topic is to try and correct this unidealness, if there's such a word. And we do this by a process called smoothing. And as the name suggests, we are going to smooth out these hills to make it easier to walk through. Now, this process takes the DC output from the rectifier. So I have my DC output from my rectifier, and I'm going to do something clever with it. Seems like all we've been doing this far is being quite clever. So this is the DC. I'm going to say specifically this is from the rectifier. Now I want to try and smooth out the graph that I was given before. So I have a positive terminal and I have a negative terminal. Now what I'm going to do is connect this across another resistor, my load resistor, my appliance that needs to be powered by DC, if you would. And so I have V out once again. I haven't really done anything here. I've simply just connected my appliance across this rectifier. So the cleverness comes from here. I'm going to connect a capacitor across the resistor. So I take this circuit, I look at the DC output, across there I connect a capacitor and then another resistor, another load, my appliance in this case, whatever it may be. Why would I do that? This capacitor has a capacitance C. Now, what happens is that this capacitor has a very special purpose. Remember what a capacitor does. A capacitor stores, air quotes again, charge, and can discharge to provide current to a circuit. So when the potential is high enough, higher than that of the capacitor charges. When the potential is low, the capacitor, being at a higher potential, will discharge automatically, spontaneously. So what's happening is, on the way up, my capacitor will charge. So my capacitor charges when the current is on the way up. Great, but what happens then? Well, the current begins to dip too much and makes it insufficient to charge my device, charge my laptop, my phone, my iPad. In the second half of that hill, on the way down, the capacitor discharges. Any of the stored charge on the plates of the capacitor gets released across this resistor. So on the way down, the capacitor discharges. So as we're coming down the hill, the capacitor discharges, any one of these hills. And this process continues. Important? Very, it turns out, because if I were to, again, as you can see, I like my graphs. They are hugely important in a topic that requires knowledge of sinusoidal motion. If I look at my V output here against time, something has changed. So I still have, or at least I had, my hills with a bit of a dip in between. What I have now done is I've actually just changed this. So on the way up, my capacitor is charging. On the way down, my capacitor discharges, and so I smoothed out the downward part of the hill a bit. The capacitor then charges again, but has to charge less, and then discharges. Capacitor charges, discharges, and this process continues. I don't go all the way down, and in that time in which, although it was a very small time, in which I had no or little current that was insufficient to do any meaningful work, I now am given that current by the capacitor. The current is now being supplied by the capacitor. If I change the values of this capacitance and the resistance, I get a different type of effect occurring. This effect, by the way, is called smoothing, because I've smoothed out the hills that I had to make it a little bit easier to walk through. Not much of a down before I have to go up again, and not much of an up as well. So it turns out that if I change the value of the capacitor and the resistance, I also get a different shape of smoothing. Now I've exaggerated this because in reality this downward part would be very tiny and almost unobservable. So the current to our eyes is basically DC. I've supplied DC current. There's a very slight fluctuation, a slight flutter, but there isn't much. And it turns out that the separation between the lowest that the current will go to and the peak value we call the ripple. Now the ripple value can change. So let's draw a different ripple value. Let's draw one where the current drops quite significantly. The pink line here is a much greater ripple, and the pink line corresponds to a small value of R times C. Now, if you remember the topic of capacitance, R times C is called the time constant. So a small time constant will result in a larger ripple. You want to use a high resistance and a high capacitance if you want a smaller ripple. And so the purple line represents a large time constant. Yes, it will take long for the capacitor to charge, but it will also hold that charge for a much longer time. And that's exactly what you want. So we've started at the, well, not at the bottom, but at the top, with half-wave rectification, where we took the AC input, turned it into DC, albeit a very poor DC signal, long times with no current. We then got a little bit smarter and we switched to full wave rectification, which required the scary looking circuit. It's not that scary once you actually read through it, redraw it, and understand what's happening. But this full wave rectification turned the valleys into hills. And now I have only hills, which is great, but I still have a little bit of a gap. You can never fully satisfy us physicists. And so we go one step further and say, well, I want to get rid of those gaps. And I do this by the process of smoothing. I take the DC from the rectifier, connect a capacitor across the external load, which is the appliance needing the DC current, and the capacitor charges on the way up and discharges on the way down. And the time constant of the capacitor, or the time constant of this RC circuit that we have here with the resistor and the capacitor, that time constant will determine the ripple, the amount by which the current begins to flutter. So this was the most difficult, in my opinion, the most difficult part about AC or alternating currents. If you read it, it does get better with time, but you make sure you're solving problems whilst you're reading as well. You can't do one without the other. So I'll see you next time for another crash course. This is Everything is Relative, and I'm Mr. K. Until next time, goodbye.